Welcome back to another video. Today we're going to be covering some math that will probably be pretty unfamiliar to a lot of you, and it involves matrices, which is a really important aspect of linear algebra, which itself is a really important part of mathematics. And we're going to be learning a few different techniques or like operations, the determinant, matrix multiplication, and the inverse of a matrix, which you'll see in our session on Tuesday are very helpful for decrypting and encrypting the Hill cipher. So we'll jump right into these. And also, it's just important to keep in mind that learning these, not only is it, can you be used to decrypt the Hill cipher, it's also just super important part of mathematics that you will find as you go on in your math careers in school and whatnot. So let's just quickly take a look at what a matrix is. A matrix is just an array of numbers that we usually write with these brackets around it. And a matrix can be any dimension, meaning it can be m by n, where m is rows, n is columns. So we can have a 2 by 2 matrix, which would look sort of like this, or it could just be any numbers. And it 2 by 2, so we had 2 columns and we have 2 rows. But it could also be 7 by 3. It could have 7 rows and 3 columns. But for our examples today, we'll just be looking at 2 by 2 matrices, because as you do more and more higher dimension matrices like 3 by 3 and so on, it's a lot harder to calculate determinants, inverses, and do matrix multiplication. Also, it's important to know that when you're calculating the determinant, you have to have a square matrix. A square matrix looks something like this. See how we have a 2 by 2, meaning the dimensions are like m by m. So you have 2 by 2, 3 by 3, 4 by 4, 1 by 1, 27 by 27, anything that's square. That's the only matrices where we can calculate a determinant. So let's get right into that. A determinant is calculated for a 2 by 2 matrix by a simple little formula. If we have this as our matrix, the determinant equals A times D minus B times C. And you'll see why. We'll explain why this is important and why you need to know how to calculate the determinant for the Hill cipher on Tuesday. But just, practice a little. Practice finding or calculating determinants of different matrices. So we'll just use a quick example. If we look at our one up here, the determinant equals 4 times 3 minus 7 times 1, which equals 5. So that's the determinant of the matrix above. Determinants are super useful in a lot of mathematics. They're used to calculate so many different things. Like when you get into more advanced mathematics, you can calculate areas with them, volumes of weird shapes. You can helps you solve equations. It's just super useful. But for right now, we're just going to look at a simple 2 by 2 matrix, and this is how you calculate the determinant, and we will use this on Tuesday. I'm also just going to show you quickly a 3 by 3 determinant, because I don't know if we'll get to it on Tuesday, but you should know how to calculate a 3 by 3, because from there you can calculate a 4 by 4 and so on. So let's just do that really fast. So if we have let's just say we have 1, 2, 3, 4, 5, 6. This is our matrix. It's an array of numbers. We have 3 rows and we have 3 columns, which remember we need a square matrix, meaning it's the same number of rows and same number of columns. Okay, so to calculate the determinant, what we do is we look at our first row, meaning 1, 2, 3. And let's start with the number 1. So we choose the number 1 and we write it down. Then we cross out with our minds. We're going to say, okay, let's not look at anything in the same row as 1. So the same row as 1, meaning this stuff right here. Don't look at that. And don't look at the things in the same column. That leaves us with a 2 by 2 matrix, 5, 6, 8, 9. We're going to multiply 1 by the determinant of that matrix. And remember how we calculate the determinant? We do 5 times 9, which is 45, minus 6 times 8, which is 48. So that's what we do. Then we write minus, because for a 3 by 3 determinant, you'll see the signs alternate in between factors. So then we take the next number in our first row, which is 2. We do the same thing. We say, let's cross out everything in the same column and everything in the same row. That leaves us with, although it doesn't look like a matrix, a 2 by 2 matrix, which is essentially just 4, 6, 7, 9, because those are the numbers not in the same row or column as 2. We're going to write down 2, just like we did for 1, times the determinant of this matrix up here, which is 4 times 9, 36, minus 6 times 7, 42. Now, like I said, we alternate signs. So at the beginning we had plus, then we had the minus right there. Now we plus again, times our last number in the first row, 3. We're going to cross out again, do the exact same thing. Everything in the same column is 3, and everything in the same row. That leaves us with a more noticeable 2 by 2 matrix, 4, 5, 7, 8. We calculate the determinant, but first we write down 3, then times the determinant. So 4 times 8, 32, minus 5 times 7, 35. If we finish calculating that, we would get negative 3 from the first parentheses times 1, so obviously still negative 3, minus 2 times negative 6, plus 3 times negative 3, which equals minus 3 plus 12 minus 9, which you will see equals 0. That just happens to be the case because we just chose a special matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9. However, that will not be the case for all square matrices, but the procedure will be the exact same. And if you remember earlier, I mentioned that once you know how to calculate a 3 by 3, you'll be able to calculate a 4 by 4 and a 5 by 5 and so on. And that's true because you'll do a similar technique. So just quickly, for example, let's look at a 4 by 4. Let's just say we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that's a big matrix, 4 by 4. I'm not going to go into it, but basically what you're going to do is a similar technique. The determinant of that is going to equal, you're going to take the first number of the first row, which gives you 1, times, you're going to cross everything out, and you're going to see that you just are left with this 3 by 3 matrix. You're going to calculate the determinant of that. It's going to go in here. And then you're going to go minus, remember to alternate, 2 times the determinant of the next 3 by 3 that you get when you cross out. So like if you cross out this row, or this row and this column, you'll be left with another 3 by 3. And you keep doing that, and then you would have plus 3, remember to alternate signs, times the determinant of another 3 by 3, and then minus 4 times the determinant of another. And that's really quick, just like you can see it's a similar technique, and that's how you calculate 4 by 4, and it should be the same. And it is the same for 5 by 5 and every other dimension higher than that. So quickly, let's just jump into how to calculate the inverse of a 2 by 2 matrix. So an inverse for matrices is basically what an inverse is for functions in normal math, which some of you may have not gotten to. And it's also similar to like the inverse for multiplication. So like if you have 4, the inverse of 4 is 1 over 4, because when we multiply them, we get 1. So for matrices, what it is, if we have A, we like to write matrices as capital letters. So let's say we have A capital as our matrix. We write the matrix, the inverse of the matrix is A to the -1 power. That -1 just indicates that it's the inverse. So when we do A times its inverse, we're going to get 1. Or in matrix talk, in the terminology we use for linear algebra, we write it as I capital. I capital is just the equivalent to the number 1 for numbers, meaning it's for 2 by 2s, it's this. Along the main diagonal, which is that diagonal from the top left down to the bottom right, we just have 1s and everywhere else is 0. So for a 3 by 3, it looks like this. Those are matrices. Those are the identity matrices for 2 by 2 and 3 by 3. And that's what we get when we multiply a matrix by its identity, just like in regular multiplication, as I showed up there with 4 times 1 over 4, where the inverse of 4 is 1 over 4, and we got 1. So now I'm just going to show you how to find, for a 2 by 2, the inverse, because for a 3 by 3, it's a lot more complicated. So for a 2 by 2, let's say we have the matrix 3, 7, 2, 1. This is our matrix, and we want to know, let's just say equals m. We want to know what the inverse of m is, so we write it as to the -1 power. So before we jump into this, I'm just going to write the general formula, and then we'll do an example. So if we have a matrix that is A, B, C, D, we like to use this as like our general. The inverse of this matrix is going to equal, so let's say this is A capital. A inverse will equal 1 over the determinant of the A. And we write this, the determinant, as A inside these like absolute value, like these straight brackets, times the matrix. And then what you do is you swap the positions of D and A. So D goes up there, A goes there. And then you just write minus for B and C. So that's a little confusing, but we'll just do a quick example. So let's look at our matrix M over here. So that means M, based on our formula, inverse, equals 1 over the determinant of M, which equals 3 times 1 minus 7 times 2. Because that's use our formula from earlier, where the determinant is just the product along the main diagonal minus the product along the minor diagonal, equal, or times, swap the positions D and A, as we saw there. So 1's going to go here, 3 there, and then just minus for the other 2. They don't get swapped though. So it looks like that. So now you're wondering, well, what do we do with this fraction outside? So we have 1 over 3 minus 14 minus 11 times this matrix 1 minus 7 minus 2, 3. Well, we can do a few things. We could leave it out there, but that doesn't really show us exactly what our inverse is. So when we have a coefficient, when we have a number that's outside a matrix, we can multiply it by every element in the matrix, meaning we can just write it as 1 over minus 11, because we multiplied 1 times 1 over minus 11. This is the matrix. So we can write it as negative 7 over negative 11, negative 2 over negative 11, and 3 over negative 11. That's the inverse of M. It's pretty messy, as inverses usually are, because we have that 1 over determinant. So that's the inverse of M. And now we're going to go into matrix multiplication, and we're going to show that M times M inverse really does equal the identity. Okay, so I wrote out, again, what M was, and now I simplified M inverse. So we have the inverse is 1 over minus 11, 7 over 11, 2 over 11, minus 3 over 11. Now we're going to do some matrix multiplication. Matrix multiplication for 2 by 2 matrices specifically, because it's a little more complicated. You follow the exact same steps, but we should only need it for 2 by 2s for our Hill cipher. You can use 3 by 3s for the Hill cipher, as you'll see on Tuesday, but for now, because matrices are pretty complicated and probably new to most of you, we're just going to stick to 2 by 2 matrix multiplication. So matrix multiplication works like this. If we have two matrices that are both square in our case, we're going to multiply the first row of the first matrix by the first column of the second matrix. So that sounds complicated, but basically what it is we're going to have, we have 3, 7, 2, 1 times 1 over minus 11, 2 over 11, minus 3 over 11. And what we're going to get is, so quickly, let's just say that we have an m by n matrix. For our first matrix, and for our second matrix we have an n by L matrix. The only reason, the only thing that we need to check when we do matrix multiplication is that the second dimension of the first matrix equals the first dimension of the second matrix. This is a little more complicated, but I'm just going to go into it for some of you who might be interested. So that just means that if we look at our first matrix, it's 2 by 2. Our second matrix also happens to be 2 by 2. So, but what's really important is that this 2 right here, which is the second dimension of our first, equals the first dimension of our second. So we could have a 7 by 2 multiplied by a 2 by 11. And when we multiply these two matrices, the dimension of the matrix that we're going to get is the first dimension of the first matrix for the first. The second dimension will be the second dimension of the second matrix, so 11. So just quickly, a little more practice. If we have a 6 by 3 matrix and we multiply it by a 3 by 5 matrix, we will get a 6 by 5 matrix as the answer, as that product between the two. So just because we have a 2 by 2, you can do the same thing and you'll see, oh, we're going to get another 2 by 2 matrix. And so the first entry of our matrix, meaning we start in the top left corner. So let's just think the top left corner, let's just write question mark for the top left. So the top left entry of our 2 by 2 matrix equals the dot product of our first row times our second column. And that sounds complicated, but it's pretty simple. So we have 3, 7. Let me write that a little better. Our first row of our first matrix is 3, 7. Why do I keep writing a dot? So 3, 7. And we call these vectors, but we don't need to go into that. So we have 3, 7, dot product, the first column, 1 minus 11, 2 over 11. So you might be thinking, wow, that's really complicated just for the first entry. Yeah, it is, but you'll see it's actually pretty simple. So the dot product works where you multiply corresponding entries. So the first entry of the row is 3. First entry of the column is 1 over 11. We're going to multiply them. Then we just add. We add the second entry of the row, 7, times the second entry of the column. And we multiply those out. And we add. We get 3 over minus 11. 7 times 2 over 11. That's just going to give us 11 over 11, which we also know is 1. So the first entry equals 1. Now let's go to our second entry in the first row. So to find the second entry in the first row, which is this question mark that I just drew in, what goes there? We take the first row again. We're going to do dot product again. So 3, 7. But this time we're going to dot product with the second column, which is 7 over 11 times minus 3 over 11. Sorry for my terrible handwriting. So dot product, you take the first entry of the first row, which is 3, times the first entry of the column, 7 over 11, because we want corresponding. So first with the first, second entry with the second entry. Then always plus times the second entry in the row, 7, times the second entry in the column. We add, so we get 21 over 11 minus 21 over 11. That gives us 0. So right there in the second entry, we will have a 0. Now let's do the third entry, which is going to be the first entry in the second row. So what goes right there? Well, this time we're going to take the second row. We're going to do a dot product the second row, so 2, 1, times the column, first column of the second matrix. So you'll notice we're always taking rows from the first matrix and columns from the second. So second row in the first, my handwriting's terrible, and first column in the second matrix. Now we're going to do dot product again. We get 2 times 1 over minus 11 plus 1 times 2 over 11. So quickly again, I'll just show you. We take first entry from the row times the first entry from the column, second entry from the row times the second entry from the column, and we add them together. Here we get 0. So right in here, we get 0. Lastly, let's do our final entry, the second row and second column. So as some of you may have guessed, we're going to take the second row from the first matrix, which we know is 2, 1, and we're going to multiply by the second column, 7 over 11 times negative 3 over 11. This is a dot product, so 2 times 7 over 11 plus 1 times negative 3 over 11. That gives us 1. I know I'm kind of going through this fast, but you can rewatch again to kind of get a grasp for this, because there's a lot of new concepts all at once. But now you'll see we finished. When we multiplied m times m inverse, we got 1, 0, 0, 1, and we just showed that that is the identity matrix, meaning it is true. M times its inverse does equal 1. It does equal the identity. So we've covered a lot of things in this video. Matrix multiplication for 2 by 2 matrices, inverses, a little property of inverses, and determinants for basically every sized matrix, but mostly we did 2 by 2 and 3 by 3. So there were a lot of things in this video, very fast paced video because we had to get through a lot. But as always, if you have any questions about anything, just email us or ask questions on Tuesday. And on Tuesday, we're going to be doing a little application of all of this, and we're going to be encrypting and decrypting the Hill cipher. So a little bit more codes for you, and I hope you enjoyed the video. As always, like I said, just email us with any questions. Thank you. Bye.